Good evening, everybody. So, today we'll simply start our discussion on ligands. And in this situation, what we have seen so far that if we have metal or anything like metal is present in solution which can interact with the ligand, giving rise to a typical complex species. So, what are these different types of ligands we can have in our hand, and which we have seen that it can be the simple water molecule to the gaseous oxygen to the most toxic gas is carbon monoxide. So, all these, that means if we just simply talk the interaction of the water molecule, the dioxygen molecule or the CO molecule with that of the metal center, and if they interact with the metal center and can modify the properties of the metal center as well as their own properties, then we can consider that these species are behaving as a ligand when they are surrounding the typical metal species. So, in this class we will see about the different classification of the ligands, how we classify most of the ligands depending upon their typical nature of binding to the metal center. So, historically when people first started talking on these and leveling all these, the term ligand was first introduced in terms of the corresponding binding property of any molecular species or ionic species, and it was Alfred Stock who introduced in 1916 in relation to silicon chemistry. So, silicon is not considered as a typical metal center, but still we know that the naturally produced different silicates and all other silicon bearing species are there. So, silicon, if we consider, is the central element where silicon is interacting with some other species which we can consider as L, then these are termed at this time as they are as the typical ligand. So, this we are discussing for the last two classes, that if we have the cobalt center in our hand, and initially when cobalt species is present in water, we have 6 water molecules surrounding this cobalt, and it has a typical geometry that we will discuss shortly, that what type of environment we can have. So, first sphere of attraction, what we have seen, the first coordination sphere of attraction is made of 6 ammonia molecules surrounding this cobalt center, and if we see from this three-dimensional figure, is a three-dimensional picture, though it is drawn in plain paper, but you see some of the bonds are facing towards the observer and some of the bonds are facing backside of this plane. So, these two ammonia, which is the bold bonds, the cobalt nitrogen bold bonds, and the ammonia molecules are also bigger in size. So, they are above the plane of the paper and these two are below the plane. And since it is not balancing any charge, these ammonia molecules are behaving as a ligand since they are binding the cobalt center. So, they are basically considered as good ligand and they are only attaching to the cobalt center from one point. That is why they are termed as monodentate ligand. and when the full coordination sphere is filled and charge is there, 3 plus charge for the cobalt center, which is getting neutralized by the presence of 3 chloride anions outside the coordination sphere. So, what we see that these ligands we can consider as monodentate ligands. So, this is basically one type of classification, that what are those monodentate ligands. So, monodentate ligands are those ligands where we have one point of attachment to the metal center. So, water molecules, these chlorides, these bromides and other halides, if they only attaching to the metal center through one point, then they are termed as good monodentate ligands. So, not only metal but also metal-like elements like metalloids, when they are bound to ligands, we see that in virtually all circumstances, when metal is in the free form as Mn plus, or metalloid also they are in the free form, they always try to bind the ligands. Even we have seen that when only water molecule is present in the solution, in the reaction vessel or in some natural environment in biological systems, these metal centers or metalloid centers will interact with these water molecules. Also, they can interact when the available group is not water molecule but a dioxygen molecule. So, metal can also interact with the dioxygen molecule, and dioxygen molecule can function as a good ligand. Similarly, the toxic carbon monoxide gas, which is a gaseous species, this can also interact to the metal center as a monodentate ligand. So, what we know that tetracarbonyl nickel species, where the nickel is in zero oxidation state. So, we have nickel in zero oxidation state, and this carbon monoxide gas can also function as a good monodentate ligand. So, starting from water to dioxygen to carbon monoxide, all of them can function as a monodentate ligand. So, when we see that these are basically also reviewed in this particular reference, the polyhedron of 83. So, there are all types of ligands have been classified, and we can see that when the ligands are present in the complex, what they do basically control the reactivity of the central atom. If the central atom is a metal, they will control the reactivity pattern of the central atom. If the reactivity pattern of the corresponding central atom is the metalloid, they can also control. So, when one particular ligand center, it can control the reactivity of one metal center. If it is iron, it can control the iron center in some form. If it is nickel, it will control the corresponding reactivity pattern of the nickel center in a different way. Also, it can control the corresponding ligand substitution rates. So, when we consider that one ligand is present with the metal center, it can be substituted by the other ligand. So, if we have Ml, and it can be Ml6 also, that means 6 ligands surrounding the metal center, and if this is reacting with Ml prime and L is substituted by L prime, then we call it as a typical ligand substitution reaction, where the ligand L has been substituted by ligand L prime, and in both these two cases the nature of the ligand, basically what type of ligand we have as L and L prime, they will control the corresponding substitution reaction. So, the role of ligand is important for this particular substitution reaction, and rate of this substitution reaction is also very important. And in some other cases, not only the substitution, but also we can talk about the electron transfer, which is guided by the nature of the ligand attached to the metal center. Then the reactivity of the ligand themselves, that means when the ligand substitution is taking place, we also find that the bound ligand which is present, sometimes the big molecule, organic molecule is attached to the metal center, and if metal is performing some catalytic role, and if we can perform some reaction on this bound ligand, we see the reactivity of the ligand, that means the reactivity of the organic molecule can also be dependent on the nature of the organic molecule, that means the nature of the ligand system as well as the corresponding electron transfer reaction. So, in different areas of this coordination chemistry, what type of ligand we are basically selecting is important. It is important, or it is critical to consider these when we try to use their choice for practical purposes. So, when we talk in terms of the corresponding bioinorganic chemistry, that means the bio-coordination chemistry, that means we want to know the corresponding nature of this metal center, what is present in all biologically important molecules, such that in the area of this bioinorganic chemistry, we all know that iron is present in our blood, and this iron is bound to a porphyrin ligand, which is a different type of ligand. We will come for the classification of that ligand also. So, when this is there, so this is the abbreviated form of the porphyrin. So, we have iron porphyrin complex, and it has two other points of attachments also, and this particular one, this ligand is synthesized in our body. So, it has some biosynthetic pathway of the synthesis. So, we get this porphyrin molecule which is attaching to the iron center. So, the role of this ligand is very important, role of this porphyrin ligand is important, and is also very much specific, because the different types of porphyrin molecules are there having different peripheral substitutions from here and from here. And for this iron porphyrin complex which is present in blood as heme is typically synthesized in our body, and it has only that particular role of oxygenation. So, it can oxygenate from this particular point, and this particular site is bound to nitrogen of the imidazolidine ring. So, this particular synthesis of this porphyrin only is important for the formation of the blood and its corresponding reactions with dioxygen molecule. So, the second is the corresponding molecules which are involved in medicinal chemistry. So, some good medicines we can have, some drug molecules are important in our hand, which basically taking the corresponding important role of the metal center to different ligand system. One such example is well known to us, basically the cancer drug, which is cisplatin, which is nothing but a platinum based metal complex. Similarly, in homogeneous catalysis, so all different types of an important catalytic reactions we can have, and these catalytic reactions are most of the cases are controlled by the metal center. So when catalysis is on, the metal center is bound to several ligand system, and those ligands also play some important role for a particular type of reaction which is giving us the corresponding reaction which is catalyzed. And lastly, the environmental chemistry. So if metal dependent environmental chemistry is available, so metal ions are also play some important role in controlling the environment. Suppose it can react with the gaseous molecules, it can react with some molecules, some deadly molecules present in water molecule size, the methyl radical also forming the methyl mercury compounds and some other type of important compounds. So wherever the metal is present, particularly from the industry, the industrial effluents, large amount of cadmium, large amount of zinc and large amount of mercury is people are dumping on the river or the ocean water, and some groups like these methyl groups or all other important groups are there which can immediately go and bind to the metal center, and they are ultimately contaminating the aquatic life, because the aquatic life, the fishes and all other species do consume all these deadly and poisonous material, and through that food chain, through that food cycle, it also comes to the human being also, and human being also by consuming those material, the fishes, they are also poisoned by these metal ions which are originally forming the metal complex. So broadly speaking, if we just consider these ligands, so how they can classify broadly in terms of their not denticity but also their charge. So if there is no charge, as we have seen just now, that if we have only water molecule or only ammonia molecule, there is no charge, so those are considered as the neutral ligand. Their size, how big they are depending upon the donor atoms, such that the donor atom can vary from nitrogen to oxygen to sulfur to phosphorus. So depending upon the donor atoms, and also if it is chelating one, that means it has two binding points, and the size of the ring is also important. Then the identity of the coordinating atoms, what type of coordinating atom we can have, the number of electrons donated to the metal through these ligands, that means how many bonds they are forming with the metal center, whether we are forming a single bond or a double bond or a triple bond to the metal center. And sometimes the steric bulk, this bulk is not related to the size of the atom from oxygen to nitrogen to sulfur, but this bulk is related to the corresponding steric bulk on the ligand and is indicated by its cone angle. In some catalytic reactions, we see one such good ligand is triphenyl phosphine. So phosphorus is there, and we can have like ammonia, 3 phenyl rings attached to this phosphorus, and the phosphorus lone pair which is there, which is being donated to the metal center. Say most catalytically important metal ion is the rhodium. So if the rhodium phosphine bond is formed and in a square planar environment, so is a 4 coordinated square planar one, and sometime this is in +1 oxidation state. So this particular one, that means the reactivity of these sites, particularly the transposition of this phosphine site and 2 other positions. So we can have the substrate and other position also reagent, and we can talk in terms of, and it has some other groups attached to this rhodium site, and these substrate and reagent can react, but the reactivity pattern will be typically controlled by the corresponding phosphine group, because this can also be occupied by another phosphine ligand also. So, this particular cone, this is a three-dimensional cone is forming, and this angle is known as the theta, which is Tolman's cone angle. So, if we vary from one system to the other, so only within the phosphine, so we can have large amount of substitutions by getting PME3, by getting PET3 and all. So, we can have different this cone angle, phosphine cone angle. So, this particular one will have some reactivity when we substitute this by trimethyl phosphine, and when trimethyl phosphine is substituted by triethyl phosphine, we have different cone angle, and the reactivity pattern on the rhodium center will also be different. So, in terms of the chelation, what we see that if we have the number of donor atoms from one point to the other, so just now what we have seen, so the monodentate ligand will be not considered as the corresponding chelating ligand, it is out of this particular list. So, like water, like ammonia, like hydroxide ion, like sulfide ion and all, they belong to this particular class. But from bidentate to polydentate system, we have more than one point of attachment. So, if we have 2 points of attachment, we get as a bidentate ligand like ethylene diamine. We can also a tridentate ligand, because most useful tridentate ligands are known. Then we can have the tetradentate ligand as 4 points of attachment, hexadentate ligand as 6 points of attachment, and these ligands can also be termed in terms of polydentate when we have 2 or more donor atoms within the one ligand system. So, they basically go for coordination to one particular metal center from 2 different points. If this is one particular donor atom and this is another donor atom, and in between if we have no other donor atom present, then we consider this as a bidentate chelating ligand. So, here we have a big list of all these, starting from the monodentate one to the polydentate groups. So, if we simply consider one after another, which is a very important thing to know, because already we have seen the amine one, and these are all monodentate one. So, this amine giving us the corresponding coordination through this red bond atom, that means the nitrogen. Then methylamine we can have, where we can have the coordination through nitrogen. Then fluoro, chloro, bromo and iodo groups are there. So, we can have all these groups, but the sizes are different from fluoride to iodide, but they only function as monodentate ligand. Similarly, this nitric oxide gas or the carbon monoxide gas, these are the two gases also. So, nitric oxide and carbon monoxide can also function as a good monodentate ligand. And from water molecule, if we have deprotonation, we get the hydroxo group, and hydroxido coordination we can have. Then NO2 minus, so sodium nitrite, if we supply to the system, sodium nitrite if we supply, this can bind to the metal ion through nitrogen or through oxygen. So, the corresponding complexes will considered as nitrito and nitrato, is that not good, it is a nitrito oxygen and nitrito nitrogen. Then we can have the cyano function, the cyano coordination. These are the two other neutral groups. We can have the pyridine, and if we have more than one pyridine groups, we get bipyridine and terpyridine. Similarly, the pseudohalide like thiocyanate. Thiocyanate can bind through nitrogen and through sulfur. So this is thiocyanate, and through nitrogen we call it isothiocyaneto, or we consider like this type of binding if we just specifically mention that which particular atom is utilized for binding, we consider this as thiocyaneto nitrogen, the other will be thiocyaneto sulfur. Then sulfato is also binding through this oxygen of the sulfato group, and when one of these oxygen is substituted by sulfur, we know that the corresponding anion is known as thiosulfate, and thiosulfato is also a very good monodentate ligand, but the charges are all different. So starting from neutral monodentate ligand to monodentate ligand, so to this monodentate binegative ligand we can have, where we have two negative charges. So when the question of polydentate ligand comes to our mind, we see that when this bidentate one, we have two nitrogen donor atoms from the ethylene backbone, and two of them are amine functions, so it is ethylene diamine. So ethylene diamine can bind through this nitrogen to the metal center and this nitrogen to the other metal center. Similarly, oxalato anion is also binding through two oxygens of the oxalate group, and this oxalate group is nothing but so two negative charges. So this particular group has two negative charges, and this is then going and bind to the corresponding metal oxalato complex. The way we determine very easily the calcium 2 plus is a very useful species for binding that as the corresponding calcium oxalate, which is a very useful gravimetric reagent, because if we have in a solution unknown amount of calcium, we add the corresponding sodium salt of oxalate anion or the oxalic acid, and at particular pH calcium oxalate is precipitated. And we filter it out. This is basically the corresponding precipitation, and if we can take the corresponding weight, we can find out the concentration of this calcium 2 plus. Similarly, one more useful polydentate ligand, it is useful for medicine purpose, for the drug purpose also, which is ethylene diamine tetraacetate anion. So if we have this ethylene diamine tetraacetic acid is abbreviated form EDTA. This EDTA is a very useful molecule. It has two nitrogen donor points and 4 oxygen donor points and 4 negative charges also. So it is basically a N2O4 type of hexadentate ligand. So this hexadentate ligand can also bind to the calcium as well as magnesium also, giving a useful Ml type of compound where the metal is there and the ligand is there in 1:1 stoichiometry. So this is the corresponding oxalate anion just now we have seen, and the ethylene diamine. So these two positions, so this is basically a charged ligand, and the backbone is of same type, but it is much more rigid because these carbons are all planar. We don't have any other distortion from that, but this cannot be planar because this carbon and these two carbons are tetrahedral in nature. So the ring, the chelate ring, what is forming through binding through these two nitrogen and binding through these two oxygens on the metal center, they are of different nature and different type. Oxalate anion can give a very rigid and very useful planar structure, but in case of ethylene diamine, it is little bit puckered. And when three such ethylene diamine molecules are attaching to the cobalt center in a three-dimensional form, so this is the only limit of this. When we will discuss about the coordination number, the possible coordination number, we will discuss once again how many donor atoms we can assemble around the cobalt center. So when we have three such ethylene diamine groups attached, so this is one ligand, this is the second ligand, and this is the third ligand, and we have a typical octahedral geometry where these two nitrogens, like hexamine cobalt 3 chloride, these two nitrogens are close to us, that means close to the viewer, and these two are away from the viewer. So these two are in a typical three-dimensional view, and we have different symmetry axis because this is a square plane, and if we view along this axis, it has a fourfold symmetry. So viewing through these symmetry points or the symmetry axis, we will find that how the different types of cobalt complexes we can have. But this is a most regular binding pattern of any first transition series or the second transition series of elements like manganese, iron, cobalt, nickel, copper, etc., where if we have a corresponding hexacoordinated complex, it basically gives us a geometry which is known as an octahedral geometry. So this is the octahedral geometry. So is basically the polyhedron is the octahedron. So next we see that when we consider all these molecules, so what we see that most of the molecules what we are talking about, what we are discussing about, either the molecule or the ion, if they are surrounding the metal center, they can function as a very good ligand. So monodentate ligand also include virtually all anions and all simple Lewis bases. So if very simple Lewis bases are there containing one good donor atom, one good heterodonor atom, they can function as a monodentate ligand. Also the halides and the pseudo halides are very useful anionic ligand, whereas ammonia, carbon monoxide and water are particularly well known common neutral monodentate ligands. So when we have the halides and pseudo halides, we see that Cl minus or SCN minus, if we try to find that whether these halides and pseudo halides, how they are binding to cobalt 2 plus. So these two will form only the tetrahedral species, not octahedral. So geometry of these species are tetrahedral. So the typical nature of these ligands, that means that chloride and the thiocyanate ligands will tell us that whenever we have cobalt available in +2 oxidation state, this is important. This +2 oxidation state, not in +3. So they basically give rise to the corresponding tetra for these such ligands, that means the chloride and the thiocyanate ligands surrounding these particular cobalt centers. So we will end up with only the tetrahedral geometry. So another type of group what we can see is related to the thiocyanate is the azide one. So azide one is nothing but is N3 minus ligand, and this N3 minus ligand can use to have 3 nitrogen atoms, and initially immediately what we can think, because it has one negative charge like hydroxide, like thiocyanate, like chloride, like bromide. So this also can form immediately to the metal center one metal nitrogen bond. So initially we will see that this can function as a monodentate ligand to the metal ion. Similarly thiocyanate also, and this particular case also, the if we can have the two tautometic geometries like these, we can have the negative charge on nitrogen and negative charge on sulfur, and what we have seen just now that this can bind to the metal center through nitrogen thiocyanate or nitrogen coordination or through thiocyanate or sulfur coordination. So, since it has 3 different donor atoms, unlike your azide, it has sulfur, it has carbon, it has nitrogen. Since carbon is sandwiched between sulfur and nitrogen, so carbon cannot go for any type of coordinating interaction to the metal center, but sulfur can, and the other end, that means the nitrogen also can bind to the metal center. So, these are also very useful ligand what we will see by binding through the sulfur as well as through nitrogen. Other organic species, they can also function as very good ligand, like when we have alcohol, that means ROH function. So, any alcohol if we can have, particularly when we use as solvent, so like water, this also has lone pair of electrons. So, when these lone pair of electrons are donated to the metal center, it can function as a very good ligand. And like water also, it can also go for deprotonation. So, methoxide ion is formed and we can have the corresponding complex of methoxo ion. Similarly, different metals also present as that corresponding metal salts of acetic acid. So, copper acetate containing 2 acetate anion and 1 water of crystallization in bivalent oxidation state. So, this is also our ligand. So, it is also coming in our ligand list, and we will discuss in our other classes that how this is CH3 COOO minus, how it is binding to the metal center, and that also will solve the puzzle related to many other metal acetates, because it is very easy to make from the other compounds like the corresponding copper carbonate. You just simply add acetic acid and after concentration and crystallization we get the crystals of copper acetate. So, this binding will be very important, but again this can function as a very good ligand to the copper center. Then the other molecules related to water, that means RH2S, that means R2O, R2S and RNH. These are the corresponding amines groups, and the substituted amines, the primary amine, the secondary amine and the tertiary amine, and the different phosphine molecules through phosphorus. So, we see that how this thiocyanate, which is a very simple reagent for reacting to any metal center, can also a very good analytical reagent to us. When we add thiocyanate, this is colorless also and this is also light yellow in color. So, when we add thiocyanate to the ferric ion, because the ferric ion present in water, we already know that it is basically the corresponding hexaacoferic ion. So, hexaacoferic ion will be there, and when we add only 1:1 stoichiometric amount of thiocyanate to the ferric ion solution, a blood red solution is developed due to the formation of this particular species, where one of the bound water molecule around iron has been substituted by thiocyanate anion. So what we get? We get a species where five of the ligands are already present like that water molecules, only one is substituted by the corresponding thiocyanate coordination as isothiocyanate coordination or thiocyanate or nitrogen coordination through iron nitrogen bond. And due to this particular reaction, this particular species giving rise a very good red coloration. So only one such bond, that means the iron nitrogen bond, will modify the corresponding electronic transition of the species. So if we go on changing the corresponding concentration of these thiocyanates, what we can see, we can substitute all other present water molecules one after another from this particular iron center, and we can substitute all the water molecules present in this particular complex species by thiocyanate anion. So if this is the octahedral geometry around this iron, so when initially we have all these as water molecules and all water molecules are still there except the one where we have one water molecule is substituted by this thiocyanate group. So we have this thiocyanate color change and we get a corresponding color change from light yellow to red blood solution. So this will be a very good reaction to know the characteristic reaction to identify the presence of iron in any unknown solution as well as the presence of thiocyanate in any unknown solution as a reagent or as an anion. So if we want to test the iron solution, we will add thiocyanate anion, or if we want to test the thiocyanate in the medium, we should add a solution of ferric chloride. Similarly, like thiocyanate, which is a 3-atom species having a charge, is going to bind to the iron center. The solvent like water, this is CH3CN, that means it is acetonitrile solvent. It is a very good solvent because it is an organic solvent, unlike your water as the solvent or methanol as the solvent. And within this particular medium, we can dissolve so many metal salts and so many ligands, because some ligands are there which are insoluble in water, which are insoluble in alcohol also. So this MECN can function as a very useful solvent, and when they are binding to the metal center, it can function as a very good ligand. So one such species what we can make in the solid state by replacing all other donor atoms around iron by MECN, and 4 such MECN will be there. For a cuprous center, copper is present in +1 oxidation state. So it is a white compound in the solid state. And if we want to prepare it as perchlorate, it is the corresponding perchlorate salt, and this is a very useful reaction to say different types of reactivity pattern related to cuprous copper, because it can activate dioxygen, it can also activate some other molecules, organic molecules, where this copper is present. This copper is bound to the 4 nitrogen atoms of the acetonitrile. So acetonitrile nitrogen, this nitrogen is also a donor atom, it also can function as a donor atom to the metal center. So like water, like alcohol, it can function as a very good ligand to the metal center. And also one more important function to this acetonitrile is that we can displace it by some other incoming ligand. So when we will study the ligand displacement reaction or ligand substitution reaction, acetonitrile should be a very good ligand surrounding the metal center. So acetonitrile will be displaced and some other new ligand system can come and bind to the metal ion. And in case of palladium, it is very easy to make this when we have the palladium chloride. It is not a very simple monomeric species, but it can be breached by chloride, so it is a polymeric compound. But when we dissolve it in acetonitrile in some hot condition, we get the corresponding species of palladium chloride with two bound acetonitrile. So it is also a 4-coordinated palladium complex where two palladium chlorine bonds are present and two palladium nitrogen bonds are there, which are due to the coordination of the acetonitrile molecules to the palladium center. So we will see next the nitrite ion, how the nitrite ion can function as a ligand. So NO2 minus can be also a very good ligand to us. And while talking about the nitrite binding, we can also think of related to something which is nitrogen bearing compound like the gaseous dinitrogen as well as the gaseous dioxygen. These two molecules can function as a very good ligand, and the reaction products of these two, that means NO2 minus, NO3 minus, NO or NO plus, all these can function as a very good ligand. And starting from the effect of nitrogenases, where we can fix this ammonia molecules we get from the dinitrogen molecule to its oxidation to different nitrogen base species, nitrogen oxide base species, we will see that these are basically going and bind to the metal center as good ligand. So during that conversion of ammonia molecules to nitrite, nitrate, NO, NO plus, if there is an intervention of the metal center, so in metal center will bind to all these species and basically go for their activation for their immediate conversion. So if we just consider the binding of the simple nitrite in the form of the nitrogen binding and oxygen binding, we know there are two types of that binding, one through nitrogen and another through the oxygen. But at least 5 different possibilities we can have. So donation from nitrogen gives the nitro complex and donation from the oxygen gives the nitrito complex. So 2 different complexes we can have. And like thiocyanate, where we have seen that thiocyanate can bind through sulfur and through nitrogen, here also it can bind through nitrogen and oxygen. So the corresponding compound, even in the solid state, the color of the compounds will be different, and they show that they can function as some ambidentate nature of the ligand. So ambidentate binding, that means 2 different donor atoms are present and 2 of them are utilized, one in one case and another in the other case, for binding to the metal center. When both the oxygen atoms can donate to the metal center, it can find its position as a chelate complex. Though it is not so easy and more examples are not there, but in some cases basically these can function as a chelating ligand by binding through both the oxygen atoms, because for nitrate it is well known, but for nitrite it is not so easy to get, but it can show the corresponding binding in chelating form. Then we can have the unsymmetrical bridge between 2 metal center donating through the nitrogen to one metal and through oxygen to the other. That means if we have this nitrogen and oxygen and this is another oxygen, so it can bridge between 2 metal centers, so it can function as a bridging ligand also to metal 1 and to metal 2. So this is functioning as a bridging ligand. So the bridge is possible, and sometimes a single oxygen atom also can bridge two metal centers. So we can have, for the substitution of the corresponding ammonia molecule from the cobalt center, we get the corresponding molecule as the corresponding nitrito complex, and the other one is also the nitrato complex. So this nitrito complex, when it is bound through oxygen, so when it is bound through oxygen, it is metastable and it can isomerize to the yellow version of the nitro complex or nitrato complex, where this particular species, that means this nitrogen, is bound to the cobalt center through this nitrogen. So these two compounds, the color of these two compounds, one is the corresponding isomeric form as the red isomer, and another is the corresponding yellow isomer. So this red isomer and yellow isomer are present due to the corresponding presence of the corresponding cobalt oxygen bond on the nitrite and on the cobalt nitrogen bond on the nitrite. So this is a similar situation where we see that the water molecules from the iron center is substituted by the thiocyanate, and it gives some beautiful coloration due to that substitution. So we can have the corresponding two isomers, one is binding through the corresponding nitrogen and another is binding through the corresponding oxygen. So this particular one, that means the red compound, and this is the yellow compound, the red isomer, where we have the oxygen of this nitrite group. Oxygen of this nitrite group is bound, and this oxygen of this nitrite group is bound to the cobalt center, and here nitrogen of the nitrite group is bound to the cobalt center. So the color is drastically changing from one to other. So these are the two isomeric form, and due to the assimilation of nitrate groups as the different nitrogen oxides, these as one of the pathways which is known to us that the metal center can bind in one form to the other and one is stable to the other. So that means if we try to activate one particular form to the other, it can go from the nitrogen coordination to the oxygen coordination or vice versa. So there are some few examples related to the classification of this ligand system. We have seen that the pyridine system, that means the pyridine like ammonia, it has donor atoms over there. So pyridine can bind to the metal center through the donation of its lone pair of electron. This is Mn plus, this is Mn plus. So the binding of this metal to this is in the monodentate fashion. So both pyridine and both ammonia can bind to the metal center in monodentate fashion for the formation of the corresponding complex. But if we go for the bipyridine ligand using two pyridine units which are in the cis position, so this is a very good bidentate ligand like ethylene diamine, and like ethylene diamine it has some rigid backbone, the pyridine type of backbone, and when it is binding to the ruthenium, when it is binding to the ruthenium, it can go for the corresponding tris complex. That means the three bipyridine units are attached to ruthenium in +2, and two chloride ions are outside the coordination sphere. It has very interesting properties. It has also very useful electron transfer behavior also, and it has some other catalytic behavior and some practical applications. So the ligand modification is important to get some important properties out of the ruthenium, which is not available if we just simply use ruthenium chloride. So some of the reactions, some of the organic transformations, we find that metal salt is added along with some ligand. Sometimes the bipyridine is added, that means the reactive species, the active species, what is forming over there is the corresponding tris bipyridine ruthenium compound, and which is beautifully red in color. Red powdered solid can be identified very easily by use of this particular ligand. Similarly, one such example of the bidentate OO donor ligand. This is NN donor bidentate ligand, but it is little bit more flexible OO donor bidentate ligand, which is acetyl acetone. So, acetyl acetone is nothing but is pentane 2,4-dione. So, is a diketone system where 2 oxygen atoms are available for binding to the metal center. When it binds to the metal center, it forms the corresponding compound like this. Like bipyridyl, it can bind to 2 such positions and it is binding through oxygen. Carbon atoms are not utilized for any kind of interaction. So, these 2 oxygens, when they are bound to this particular metal center in the octahedral form, in the manganese acetyl acetonate compound. So, usually it is stabilizing the trivalent manganese, because after deprotonation it gives us through the keto-enol tautomerism 1 negative charge. So, ligand is bidentate mononegative ligand and it is stabilizing manganese in +3 oxidation state. Similarly, it can stabilize vanadium center with the vanadium oxo center, then in the vanadil center by binding in a different geometry. This geometry is different from that, which is a square pyramidal geometry, which is VOACAC2. So, this is the acetyl acetone ligand, which is present with manganese as the tris manganese compound in the octahedral geometry, and in vanadil system it is in the VOACAC system in a square pyramidal geometry. So, we will see more of these type of examples in some of these classification of these ligands, and what are the more and more complex ligand systems we can have. Ultimately, we reach to the biological system where biological ligands are much more complex to bind to the metal center. Thank you.